So hello and good morning to everyone. So our today's lead code question is 2685, which is count the number of complete components. So basically in this question we are given an integer n which denotes the total number of nodes present in the graph, right? In the undirected graph having n vertices, and the number and the vertices are from 0 to n minus 1. So with that we are also given a 2D integer array named as edges, where edges of I is equal to ai bi. So this will denote that there is an undirected edge between the nodes ai and bi, right? So now what we have to do is we have to return the number of complete connected components of the graph, right? So first let's see what is a connected component and then what is a complete connected component. So a connected component is basically a subgraph of a graph in which there exists a path between any two vertices, right? And no vertex of the subgraph shares an edge with the vertex outside the graph. So if you see the example, so this is a graph. So we can see the graph is having one part over here and the other part over here. So basically these are two connected components, right? And between two connected components there is no edge between two connected components, right? So now if you see we have two connected components over here, and now a connected component is said to be complete if there exists an edge between every pair of its vertices. So first if you see this connected component, there is no edge between 4 and 5. There is no edge between the vertices 4 and 5. So this connected component, it is not complete. This is not complete, right? But if we see here, there is an edge between 0 1, 0 2, 1 2, 2 0. So all the pairs of the vertices have an edge between them. That means this is a complete connected component, right? So let's see the examples to understand the question more clearly. So here we are given this graph has two two connected components two connected components. Now out of those two connected components, how many are complete? That we have to check how many are complete, right? So a complete connected component is that component that have edges between all the pairs. So suppose if a connected component has k vertices, so for it to be complete connected component, each vertex should be connected to all the rest of the vertices. So that means each vertex should be connected to all the k minus 1 vertexes, right? So suppose here we have three nodes. So each vertex should be connected to all the k-1 means two nodes. So here 0 is connected to rest of the two nodes, then 2 is connected to the rest of the two nodes, 1 is connected to the rest of the two nodes, right? So in this way a complete connected component has how many total edges? So if it has k nodes, then each node will be connected to k-1 vertices, right? Each node will be connected to k-1 vertices. So the total degree of this connected component will become k into k-1. And as we know, each edge is shared between two nodes, so the total number of edges should be k into k-1 by 2. So if a connected component has k into k-1 by 2 edges, where k is the number of nodes in the connected component, then that connected component will be a complete connected component, right? So here we see k is equal to 3, then how many edges should it should have? It should have 3 into 3 minus 1 by 2, that is 3 edges. Does it have 3 edges? Yes. So it is a complete connected component. Then we'll check for this. Again it has 3 edges. It has 3 vertices. K is equal to 3, then it should have 3 edges, but here it has only 2 edges, so it is not a complete connected component. So our answer is 1, that there is only one complete connected component. So let's move to the constraint part. So here n can be from 1 to 50, that is at max we can have 50 nodes in the graph, and the number of edges in the graph can be n into n minus 1 by 2 in the worst case, and edges of edges of I dot length is equal to 2, that is it has two components ai and bi, that is there is an undirected edge between the nodes a and b, and ai and bi can take any value from 0 to n minus 1, as our nodes are labeled from 0 to n minus 1, and ai is not equal to bi, that means there is no self edge, there is no self edge, or there is no self loop, right? And there are no repeated edges, that means if there are two nodes, then there is only one unique edge between those two nodes, right? So these are the constraints. So let's move to the approach part. So as we know, what we need to do is we need to count the total number of complete connected components present in the graph. That is what we have to count. So first, so to fulfill our this goal so to fulfill our this goal, first what we'll do is, first we check the total number of connected components. First we'll find those using BFS and or DFS. So first using BFS or DFS we'll find the connected components, right? And once we get the connected components, then we check that whether those connected components are complete or not, right? And how do we check that? So to check that, if they have k nodes, then they should have k into k minus 1 by 2 edges, right? If the connected component has k nodes, then for it to be complete connected component, it should have k into k minus 1 by 2 edges. So if they have k into k minus 1 by 2 edges, then it will be complete. So we increment our answer. So this will be our overall approach. So first let's see how we'll find the connected component in a graph, right? So here we'll be using BFS to find the connected component in the graph. So first of all, what we'll do is we'll start iterating from the vertex 0 to n minus 1, and then we check if the vertex has not been visited or it hasn't been marked as visited, that means we have found a new connected component. So using that vertex which is unvisited, we'll start BFS from that vertex, and then we will try to reach, then we'll go to all the vertices which are reachable from that starting vertex, right? So all the vertices which are reachable from that starting vertex will be part of that component, will be part of the same connected component, right? So we mark all the vertices that are reachable from that starting vertex as visited, so that we do not process them again. And when we are doing the and when we are applying the BFS, at that time what we'll do is we'll keep track of the number of nodes, that is the number of vertices that are present in the connected component. So we'll store that also, and with that we'll also store the edge count, which is basically the sum of the degrees of all the vertices in the current connected component. So we count two things: the number of nodes in the connected component, and the edge count, which is basically the sum of the degrees of all the vertices in the current connected component, right? So now as we know, a complete graph with k vertices has k into k minus 1 by 2 edges, right? So when we are checking, so when we are checking the or when we are finding the connected component, at that time we have stored the nodes, which is basically k. Also we have stored edge counts, which is basically the degree of the vertices. And as we know that in an undirected graph, two nodes share the same edge. So whatever degree that we will get, so that degree by 2 will be the total number of edges, so to find the total number of edges, what we'll do is we'll do edge count by 2, and then we know the number of nodes. So number of nodes is stored in nodes, so the total number of expected edges will be nodes into nodes minus 1 by 2. So this should be the number of edges the component should have for it to be complete, right? And what is the total actual number of edges? That is edge count by 2. So now if the expected value and the actual value, then we compare the expected value and the actual value, and if they are equal, if the expected value and the actual value are equal, then that means our current connected component is complete. So in that case we increase our answer by 1, else the current component is not complete, so then we find the next connected component. So now we'll try to understand the whole approach with the help of an example. Here in this example we have n is equal to 6, and this is a as is 2D matrix, right? So first of all, the first step that we do is we build the adjacency list from the edges, right? So we have built the adjacency list, right, using the as is 2D matrix, right? And then once we build the adjacency list, then we'll start, then our steps will be find the connected component, using BFS, and then in the BFS we'll count the number of nodes and the edge count, and then using nodes and edge count we'll check whether the graph is complete or not, right? So this will be our overall approach. So for that we have a visited matrix in which initially all the nodes are unvisited, or all the nodes are marked as false, that is they are not visited, and our answer is equal to 0. Now what we'll do is we'll scan this matrix, this visited array, and then once we get an unvisited node, so we'll take that node, and then we'll start BFS from that node. So initially we'll start BFS from the vertex number 0, because that is unvisited. So we push the node 0 into the queue, and then as we see, our number of nodes is 0 initially, and edge count is 0. So now initially our queue has node 0. So first we visit node 0. So in that case our number of nodes will become 1, and the edge count, which is basically the degree of 0. So degree of 0 is connected with, in 0 we have two neighboring nodes, 1 and 2. So edge count will be plus 2, so it will become 2, edge count will become 2, right? And then what we'll do is, then we push the unvisited neighbors of 0 into the queue. So both 1 and 2 are unvisited, so now we push them into the queue, and the queue will become this, right? So then next we have marked 0, 1 and 2 as visited. Then what we'll do is, then we visit 1, so then we remove 1 from the queue, so in the queue only 2 is left. So now the number of nodes has become 2. edge count was 2, and so as we know, 1 is connected with 0 and 2. So again we add the degree of 1. So degree of 1 is 2. So we again add 2 to the edge count. So edge count will become 4. And neighbor of 0 and 2, neighbor of 1 are 0 and 2, and they are already visited. So we do not push anything into the queue. So now in the queue we are left with only 2, right? So now we visit 2. So now when we visit 2, we remove 2 from the queue, so the queue will become empty. Now the number of nodes that we have checked are 3, and as we know 2 is connected with 0 and 1, so the degree of 2 is 2, right? So we add that degree also with in the edge count. So now our edge count will become 6. So now there is no new neighbors that are unvisited, so that means the BFS has finished. That is from the node 0, we can only visit these three nodes, or these three vertices, that is 0, 1 and 2. So that means these three will belong to one component. So in the current component we have get vertices as 0, 1 and 2, and the number of nodes is 3, and the edge count is 6, which is basically the degrees, sum of the degrees. And now as we know, every edge is counted twice, so the actual number of edges is as count by 2, that is 6 by 2. So the number of edges that we get is 3, right? So as we know, the nodes is 3, and the total number of edges is 3. So now how many edges it should have for this to be complete? That is k into k minus 1 by 2, that is 3 into 3 minus 1 by 2, which is 3. So the expected number of edges should be 3, and the actual number of edges are also 3. So both are equal. That means this component is complete. So our answer will become 1, right? That is, we get one complete component. So now then we next will find the next component. So we see node 1 and node 2, they are already marked as visited. Then we move to node 3. So node 3 is unvisited. So then we start BFS from this node, and as we know 3 and 4 are connected. So after processing the BFS, we'll get the vertices as 3 and 4. Nodes will be 2, and edge count is 2. So now this edge count is basically the sum of the degree. So we'll half it to find the actual number of edges. So the actual number of edges is 1, which is 3 and 4, this edge, right? And the expected number of edges should be total number of nodes, that is 2, so it will become 1. So actual edges are 1 and the expected number of edges are 1, so both are equal. That means this component is also complete. So our answer will become 2, right? And then the next unvisited node is 5th. So node 5 is unvisited. So again we start BFS from this node, right? But this is a only one node, this is not connected with any other node. So after BFS we get nodes is equal to 1 and edge count is 0. So the total number of actual edges is 0 and the expected edges is also 0. Now again both are equal. That means this component is also complete. So the total number of complete connected components are 3. So our final answer is 3. So even if we see in this graph, this is one component, this is one component, and this is one component. So we have 3 components now, which if we check, this is also a complete component, this is also a complete connected component, and this is also a complete connected component. So total we have 3 complete connected components in the example, right? So this way we'll find the total number of complete connected components. So first we find a unvisited node, then we apply BFS from that node, and then we'll find the number of nodes and the edge counts in that component, and then using those we'll check whether that what we call that connected component is a complete connected component or not. So let's see the code part. So in the code part, first we'll build the adjacency list, and then we have taken a vector visited in which initially all are false, false, and our answer is equal to 0. And then we start iterating from I is equal to 0 to all the nodes up to n minus 1. And if the node is already visited, then we skip that node. Else we start BFS from the node. If the node is not visited, then we start BFS from the node and push that node in the queue and mark it as true. And then we have two variables, nodes and edge count. So nodes will, in the nodes variable we will store the total number of nodes in the component, and then in the edge count we will store the total degree of the nodes in the component. And then until our queue do not becomes empty, so we have here we will apply the BFS. That is, we try to reach all the nodes which are reachable from the starting node. So after this we'll get the number of nodes in the current component and the degree and the total degree. So to find the total number of edges, we'll divide the total degree by 2, because each edge is basically shared by two nodes, right? So the total number of edges edge count by 2. Now we have to check whether this component is complete or not. So for that, the actual edges should be equal to total number of nodes is k into k minus 1 by 2. So these both should be equal. So if this condition holds, that means our current component is complete. So we increment our answer, and at the end we return the total number of complete connected components in our answer. So I hope I am able to explain you the solution properly. So if you like the video, please make sure to like, share and subscribe the channel. Thank you.